Hi again, JF with you today to discuss the Poisson distribution, which is a distribution law within the discrete random variables. A Poisson variable is characterized as being a rare events experiment. Unlike the binomial and the hypergeometric, which have very specific features, the Poisson is harder to describe, and we will usually just tell you a variable obeys a Poisson law. We say rare events because, for example, every person who walks by the Toronto Dominion ATM machine at the corner of Sherbrooke and Claremont will not necessarily use it. Every passer could be considered a trial, and those who actually use the ATM machine would then be considered successes. So this could be perceived as a binomial or as a hypergeometric. However, if the probability of a success is very, very low, in this case, for example, 1 out of 200 trials, perhaps we want to use a different law. A Poisson variable is therefore rather defined by a number of successes per time period. To label a variable that obeys a Poisson distribution, whose average per time period is lambda, we will write that x follows a Poisson distribution of average lambda. For example, let's suppose the number of students who consult JF during a given office hour varies according to a Poisson distribution, with average 3 visitors per hour. If x represents the number of students who consult JF during that given hour, then x obeys a Poisson of average 3. Here's another example. Suppose every 20 minutes, 120 people walk by the TD ATM machine at the corner of Sherbrooke and Claremont. 1.5% of passers will typically use the ATM machine. So according to a binomial law, we would expect that 1.5% of the 120 passers will actually use it, and that means 1.8 ATM users per 20-minute period. So using y as being the number of ATM users per 20-minute period, x obeys a Poisson of average 1.8. As for previous discrete variables, we have formulas to represent the expected value, the variance, and standard deviation of a Poisson distribution. So for a Poisson distribution, its expected value is its average, so lambda. The variance actually turns out to be lambda as well, and therefore the standard deviation is the root of lambda. If you had to calculate the probability for a specific value of variable x, in the case where it obeys a Poisson distribution, then we have a probability function. So the probability that x will take on a specific value k is given by the expression on the right. Lambda is still the average value of the Poisson law. As you can guess, we will not prove this formula, but rather use it. Here is what a Poisson distribution of average 1 would look like. As you see, most of the weight is distributed near 0, so very few successes should be observed by time period. A Poisson of average 4 will be quite delayed compared to the Poisson of average 1, with much of the weight around 3, 4, and 5. Some exceptional cases where we get all the way to 10 or no successes at all are also possible, but not as likely. You can calculate probabilities on your calculator, or you can use a table, but if we have access to Excel, we'll rather use the integrated statistics functions that it has. This one would be called a loi de Poisson, or in your English version, a Poisson dist. In Montreal, let's assume the number of days when more than 20 centimeters of snow falls obeys a Poisson distribution of yearly average 3. So notice we're using a year as a time period, and a success would be a snowfall of over 20 centimeters of snow. If X is the number of days in a year where more than 20 centimeters of snow fall on Montreal, then obviously X is a random variable. On a given year, there might be no such days, or there might be 9 days where more than 20 centimeters of snow would fall. So X is definitely a random variable. We would label X with the probability notation that follows. So in this case, X obeys a Poisson distribution of average 3. Again, time periods here are counted as years. What is the expected value and standard deviation of X? Well, for Poissons, it's actually quite straightforward. The expected value is 3, and so is the variance, and therefore we would expect 1.89 to be the standard deviation around the expected number. So snowfalls that accumulate more than 20 centimeters of snow are more likely to be between 1 and 5. What is the probability that exactly 4 days will produce more than 20 centimeters of snow in a given year? We have our formula in order to calculate this probability, and that is if we don't have access to a data form instead. And of course we have Excel that can tell us the probability for this specific X value. Now if we were wondering how probable 2 or more days will produce more than 20 centimeters of snow, 2 or more is actually the opposite of 1 or less. Most probability tables are given for values that are specific and those that precede it. So what we call a cumulative probability. And this is also one of the highlights of Excel, where we can, in the bottom window, specify we want to accumulate probabilities all the way to 1 in this case.